But I actually think we're kind of on the edge right now. Maybe everything goes really well and we get this incredible prize. A world where everyone you love is safe and free. I hope so. Or maybe we get it wrong and we end up releasing powerful and opaque systems that we cannot meaningfully control or predict. Or understand the children of the increasingly powerful and increasingly opaque systems that we're building today. The systems that we don't really understand today. My background is in AI for histopathology, and the academic literature is full of AI models that, on average, outperform doctors and pathologists at various different diagnostic tasks. It's a difficult task, but it's not actually that difficult, like building an autonomous car that is, on average, safer than a human driver. We're pretty much there, right? So why did a human drive me here? The problem is edge cases. Unexpected failure modes and unexpected biases in our models. We don't understand our models well enough. And we don't understand them well enough to predict how they'll behave on edge cases. And we don't understand them well enough to validate that they've learned sensible features from the data. We don't understand them well enough to really trust them in high stakes domains yet. And that's where LEAP comes in. Yeah, oh, thank you. LEAP, we are a research-driven AI interpretability startup, and we're putting robust, model-agnostic, data-independent interpretability tools in the hands of every AI developer. That's the plan. The model-agnostic part is simple. Our methods work on all differentiable models. It doesn't matter what your model architecture is. We can directly compare convolutional networks, transformers, whatever next year's big architecture might be. We're not just visualizing filters here. Our methods can also be applied across different modalities. We can work with language models, tabular data, time series, video. It's all model agnostic. But today I'll focus on computer vision because that's what you guys are into. Data independence as well is key. Typically, we try to predict the deployment performance of a model, understand what it's learned and where it's weak by looking at various metrics over its test performance on some holdout test set. And that's definitely useful, but there are no guarantees that the test set contains all possible edge cases or failure modes. So at LEAP, we're taking a different approach, and we're asking a different question. What's goldfish? Well, this is goldfish, according to ResNet 18. More precisely, this is what a ResNet 18 model trained on ImageNet thinks is the most goldfishy goldfish ever. The prototypical goldfish, if you will. And we're extracting this class prototype directly from the model. I've removed repeated patterns and extraneous stuff in this example. Typically, we generate prototypes like this. This is maximum goldfish. And we can do this for any class, or any combination of classes. We can ask other questions too. What's the opposite of a goldfish, according to ResNet 18? Whatever that thing is. What's the minimum goldfish? What's the least thing, the smallest thing that would still be considered a goldfish with 100% confidence by this model? That thing. We can also identify and quantify if a class prototype shares features with prototypes of other classes. So which classes overlap? This is called class entanglement. You can maybe just about see this chart, which shows the entanglement of every other ImageNet class with the goldfish class. Identifying entanglement can help us understand when and why a model might make mistakes on unseen data. Highly entangled classes are more likely to be confused because they share a lot of features. Underneath here, I've generated the prototypes for the 4 classes that are most entangled with Goldfish. And you can see their entanglement scores with respect to Goldfish class. And if you're curious, Wikipedia tells me that an F is a newt in its terrestrial juvenile phase. So if you take nothing else away from this, there you go. We can also isolate how the classes are entangled. Here you can see which features, which parts of the Goldfish prototype are shared with these other classes. And the beautiful thing is, if we do this for every class that a model predicts, we can build up a taxonomy of all the features that a model has learned. We can see everything that it knows. And because our methods are model agnostic, we can really easily compare different architectures. This is kind of important because often different models will learn quite different prototypes with different entanglements, even when they're trained on exactly the same data. So this can be pretty useful to identify the trade-offs that you're making in terms of what the model is able to learn when you're selecting an architecture for a particular use case. And interestingly, notice how the vision transformer is actually quite different to the convolutional models. Here's a real-world example. These prototypes are from a model that was trained to recognize 15 different human activities: laughing, texting, sleeping, everything that humans do. It was trained on about 1,000 images, so not a huge training set, and it's about 80% accurate on validation, not trained by me. I don't take credit for this one. Looking at these prototypes, we notice a few things. We've got a nice bike there for cycling, laughing, mildly terrifying. Listening to music, like, this is really confused and noisy. There's maybe some headphone cable there, but I would suspect that this model probably isn't very good at recognizing people listening to music, or using laptops. Either that's pretty indistinct. Kind of troublingly, really, if you look at the skin tones on dancing and fighting compared to the other classes, it looks like maybe this model thinks only darker skinned people dance and fight, which is not great. Running as well seems a bit suspicious. It looks like it's using mostly grass and foliage kind of textures. And it also looks like this model hasn't used the action, hasn't learned the action, the activity of eating very well either. It's learned to look for food instead, which makes sense. Finally, this is the last one. This is a real-world example in a slightly higher stakes domain of cancer detection. I just pulled this model off Hugging Face. It's actually the same architecture as before, but it's been fine-tuned. It's a vision transformer, and it's been fine-tuned on about 25,000 histopathology images up there to give you a sense of what they look like if you're not familiar with these kinds of images. There are 5 classes there. Two are benign, healthy, lung or colon tissue, and the other 3 are cancerous. And here at the bottom, I've generated the prototypes for each of these classes. This model is actually over 99% accurate on the hold-out test set, and we can see why. If we look at the entanglements that I've plotted here, the prototypes don't overlap at all. There's no entanglement at all. The prototype for one class doesn't cause the output for any other class to increase. In fact, it causes the output for all of the classes to decrease. So even without any domain knowledge, you don't need to be a histopathologist to see that this is a very confident model with really clear separation between the different classes. And that's pretty much all from me. A couple of last things. We're hiring. We would really love to hire a lead product engineer. We're hiring for our engineering and products and research teams over the next few months, but we're immediately focused on finding an exceptional person to basically own turning this research into a fully fledged, beautiful, intuitive, really, really useful interpretability tool that helps everyone understand their models better. If that could be you, please come and talk to me. Or my wonderful co-founder Jugal, who is
right here,
right there. And finally, We have a design partnership program. We're looking for a few more design partners to consult with us as we build this product, to help us build like the most useful thing we can from this research, and also to inform our like ongoing research directions too. So if you're building computer vision models and you would like to understand them better, you can sign up here using this QR code or come and talk to me or